In a world just overflowing with information, wouldn't it be incredible to have a shortcut? A way to truly understand groundbreaking innovations, to move beyond just the headlines and really get to the why and the how. Well, that's exactly our mission today. We're diving deep into a really fascinating story. It involves a self-taught innovator and a company called DeMoD. We're going to unpack DeMoD's cutting-edge technology, from its unexpected origins in high-performance audio to its surprising and honestly far-reaching applications across multiple industries. And this isn't just about, cool tech for its own sake. It's about how accessible, incredibly low latency, and truly open source solutions are poised to fundamentally transform, well, everything. From how your car gets diagnosed, how we monitor health, and even explore the farthest reaches of space. We're really talking about a potential paradigm shift in how we gather and interpret data.
Indeed. And we have a rich stack of sources for this deep dive, giving us a really comprehensive look. We'll be pulling insights from detailed design specifications of an innovative communication framework, exploring the nuances of a pretty unique and multi-purpose hardware device, and delving into comprehensive briefings on how these components sort of coalesce, how they come together to create what you could only describe as a universal diagnostic platform. You'll hear about the bold vision behind these tools and the tangible, often quite disruptive benefits they promise across sectors like automotive, manufacturing, healthcare, IoT, and yes, even aerospace.
Okay, so if you're ready to get truly well-informed on a remarkable innovation story, and maybe discover how one company's approach to technology could deeply affect your world, let's unpack this.
The genesis of innovation, Asher Leroy, and DeMoD's core technology.
All right, let's start with the remarkable individual, right at the heart of this whole innovation, Asher Leroy. What stands out immediately, and is pretty profound, is his journey. I mean, a completely self-taught cybersecurity innovator and full-stack developer who bootstrapped DeMoD Ltd. By the impressive age of 21. Think about that for a second. Nearly a decade of hands-on, highly technical experience, mostly as a solo developer, before many people even finish college. That's not just about technical skill, right? It speaks to an incredible drive, maybe an unconventional approach to solving problems.
Yeah, what's truly fascinating here isn't just the age, although that's remarkable enough. It's the sheer breadth and depth of his early foundational achievements, things that very clearly foreshadow DeMoD's later trajectory. Consider this. Asher developed the entire DeMoD.ltd website in just 12 days.
No, the whole site.
The whole site on a virtual private server using Docker. And it wasn't just, slapped together. It achieved really impressive page speed insight scores, performance 94, accessibility 89, best practices 100, SEO 82. I mean, these are metrics that many large professional development teams might strive for over months. It just showcases an incredible capacity for rapid, high-quality, full-stack development right from the start. But it gets even more interesting when we look at Archibald OS.
Archibald OS, that was a Linux distribution, wasn't it? What was special about that one?
Exactly. Archibald OS wasn't just another Linux distro. It was specifically engineered, optimized to reduce audio latency by an incredible 30%. And the goal was sub-3 millisecond real-time audio effects.
Sub-3 sheeps. That's incredibly fast.
It is. To put that in perspective, this rivals even Apple's Core Audio.
Which is often seen as the gold standard, right?
Precisely. The gold standard for low latency audio performance. And the significance here is kind of twofold. First, it demonstrates a really deep understanding of system level optimization, real-time processing, laying the groundwork for DeMoD's later work with digital signal processors, or DSPs. And second, it highlights Asher's ability to get these high-performance results using open source tools, which is a philosophy that, deeply underpins DeMoD's whole approach. These aren't minor feats. They really speak to a profound capability for rapid, high-quality development and integration across diverse, complex technical areas.
Okay, so we have this picture forming. A prolific, self-taught innovator, really focused on performance and efficiency. Let's unpack DeMoD's core technology then. You mentioned it didn't start with a general communications framework. It began with something highly specialized, the DeMoD Secure Protocol, or DSP.
Yes, and that origin is absolutely crucial. You really have to understand that to see where DeMoD is going. The original DeMoD Secure Protocol, DSP, was designed with state-of-the-art AES 256 GCM encryption.
Okay, that sounds serious.
It is. It's a very robust military-grade standard. And crucially, it was ITAR regulated.
ITAR. What does that mean exactly?
Right. So for listeners who might not know, ITAR stands for International Traffic in Arms Regulations. Essentially, it meant the technology fell under strict U.S. government export controls for defense-related items and services. This classification profoundly influenced its initial design, signaling its intent for highly sensitive defense and high-tech applications. Asher even secured a provisional patent for it and submitted it for a USF SBIR grant. That's a Small Business Innovation Research Grant.
Ah, okay.
Now, while it wasn't ultimately selected for the grant, it was deemed technically viable.
Which is still a pretty strong endorsement.
Absolutely, a strong endorsement of its robust, high-security foundation. This whole origin story speaks to a deep understanding of cybersecurity and secure, mission-critical communication embedded right from the very beginning.
Okay, so from this defense-grade, ITAR-regulated beginning, we then see this evolution to what's now called the DeMoD Communications Framework, or DCF. What exactly is DCF, and I guess why should someone listening care about a communications framework? It still sounds a little abstract.
Well, what's truly fascinating here is the strategic pivot. It's a really smart move. The DeMoD Communications Framework, DCF, is essentially a shareware, free, and open source software FOSS version of that original, highly secure DSP. It was deliberately released under the GPL v3 license. The goal was to foster community growth and, critically, to sort of democratize access to this incredibly robust underlying technology.
Right, make it available.
Exactly. And why should you care about a communications framework? Because it provides the foundation, a modular, interoperable, and really lightweight foundation for low-latency data exchange in general-purpose applications. This means it's the invisible backbone for real-time communication that powers so many things we rely on today, often without realizing it.
Like what sort of thing?
Well, think about its potential in IoT messaging, for example. Countless devices, smart home sensors, industrial machinery. They all need to communicate efficiently and reliably. Or think about real-time gaming synchronization. Every millisecond of lag matters there, right?
Oh, yeah.
DCF is vital for that. It's also crucial for distributed computing and edge networking, where data needs to flow seamlessly across many nodes without bottlenecks getting in the way. It's basically about making high-performance, secure-by-design communication accessible and adaptable for pretty much any modern networked application, far beyond just its defense origins.
And what makes it so performant? I'm seeing terms in our sources like handshakeless design and sub-millisecond exchanges. How does it actually manage that speed and efficiency?
Yeah, that's a key differentiator. Its handshakeless design minimizes those negotiation delays you usually see. In traditional communication protocols, there's often this back and forth, a handshake process.
Like, hello, you there? Yeah, I'm here, that kind of thing.
Exactly. It's sort of a, hello, are you ready? Yes, I'm ready. Here's my ID setup phase before data can even start flowing. By largely eliminating this, DCF becomes incredibly efficient. It cuts out those crucial milliseconds of delay. This is absolutely critical for real-time applications where every moment counts. It targets sub-millisecond exchanges with less than 1% overhead.
Less than 1%, that's tiny.
It is. Very little of the network's capacity or the device's processing power is wasted on the communication protocol itself. This efficiency comes from a few clever techniques. Efficient data serialization using protocol buffers.
Okay, protocol buffers.
Yeah, it's a language-neutral, platform-neutral way to structure data efficiently. And it has a unified compatibility layer that bridges various transports like UDP, TCP, WebSocket, and gRPC. Plus, it supports seamless peer-to-peer, or P2P, networking with quite sophisticated self-healing redundancy mechanisms.
Self-healing, what does that mean in practice?
It means if one path or node in the network fails, DCF automatically finds another route. It can recover from failures in dynamic environments. Think mobile networks or IoT deployments where things change. And it does this with impressive round-trip time, or RTT-based grouping, keeping communication clusters under 50 milliseconds latency, even during recovery. That's very fast, ensuring continuous operation.
That sounds incredibly flexible, supporting so many different transports, being able to self-heal. But with such broad compatibility across hardware, languages, and transports, how does DeMoD even ensure consistent performance and stability? Especially, in resource-constrained environments. Or are there specific cases where developers might face optimization hurdles?
That's a very astute question, and it really gets to the heart of DCF's architectural brilliance. DCF places a strong emphasis on being hardware and language agnostic. That's a significant differentiator. This means it supports deployments from even the most resource-constrained embedded devices like, think tiny sensors in an IoT network.
Microcontrollers and things.
That's exactly. All the way up to high-performance cloud servers and mobile platforms like Android and iOS. It's designed to be implemented on pretty much any hardware architecture, ARM, x86, mobile sauces, and in a remarkable array of programming languages. We've seen examples for Perl, Python, C, C++, Node.js, Go, Rust, Java, Swift.
Wow, that's a wide range.
It is. This broad support, coupled with robust cross-platform interoperability thanks largely to protocol buffers and gRPC, ensures developers aren't locked into specific ecosystems. That's a huge win for flexibility and adoption. Now, regarding stability and optimization, the unified compatibility layer actually abstracts away much of the underlying complexity. It provides a consistent API regardless of the transport or hardware being used underneath. While, yes, every environment presents its own optimization challenges, DCF's lightweight design means it provides a highly optimized starting point. Performance tests really highlight this efficiency. They show under 1 millisecond for local exchanges.
Under 1 millisecond local.
And minimal CPU usage, often less than 5% on devices like a Raspberry Pi.
That's really low.
It makes it uniquely ideal for embedded systems or battery-powered devices where every bit of power, every milliampere counts.
But okay, what about security? Given its origins in defense as the DeMoD secure protocol, and now the shift to an open source model, has that strong security posture been maintained? What are the implications of it intentionally not having built-in encryption? That seems like a big change.
This raises an extremely important point, and it ties directly back to those ITAR regulations we talked about. As a FOS shareware version, DCF intentionally does not have built-in encryption. And this was a deliberate, strategic decision made specifically to avoid those export controls that applied to the original proprietary DSP.
Ah, okay. So if it had the encryption, it couldn't be easily shared globally.
Precisely. Had DCF included that military-grade encryption by default, it would have been subject to the same strict regulations, severely limiting its open-source adoption and global accessibility. So instead, DCF relies on users, on developers, to extend its security by integrating standard, widely available security protocols.
Like what?
Well, developers can wrap it with TLS-D, TLS. These are the standard security layers used for secure web browsing, HTTPS. Or they can leverage gRPC's inherent support for secure channels via TLS, which is particularly suitable for mobile applications where end-to-end encryption is really paramount. So while it doesn't include the original military-grade encryption by default, it does include basic protections. Things like timestamp validation against replay attacks that prevents malicious resending of old data.
Right.
And sequence numbers for message ordering, which helps ensure data integrity. The strong recommendation, especially for production environments, is always to run DCF over secure transports like secure WebSockets, WSS, or secure gRPC. And users are encouraged to add application-level authentication if needed, maybe using custom protobuf fields or gRPC interceptors. It's really a pragmatic trade-off. Prioritizing open access and widespread applicability while providing robust mechanisms for users to add the necessary security layers for their specific needs.
Okay, that makes sense. A strategic trade-off for accessibility. So we have this robust communications framework, DCF, that's incredibly fast, flexible, and strategically designed for broad use. But DeMoD also developed a unique piece of hardware, a multi-purpose USB DSP audio device. And initially, this was designed primarily for audio applications, is that right?
Correct. And this device is where the hardware innovation really comes into play. It's not just software. It's built on high-performance Texas Instruments digital signal processor, or DSP PCBs, using specialized components like the TMS 320 C674X series, which can run at up to 300 megahertz.
And DSPs are different from regular CPUs, right? They're specialized.
Exactly. They are purpose-built for crunching numbers in real time, perfect for complex audio and signal processing tasks. So this device is designed for real-time audio processing, offering superior sound quality and remarkably low latency, typically less than 5 milliseconds. But a key benefit, one that's often overlooked, is that it offloads CPU-intensive tasks from the host device.
The computer or console it's plugged into.
Right. Whether that's your computer, a gaming console, or even an embedded system. It reduces the host's CPU load by a significant 20-30%.
Wow, that's quite a bit.
It is. It frees up the host device for other tasks, improves overall system responsiveness, and here's where it truly becomes disruptive: the price. It's incredibly affordable, priced at just $50 to $100.
$50 to $100 for that kind of performance.
Exactly. This allows it to directly compete with premium audio interfaces costing $200 or much more. It really democratizes access to high-end audio processing capabilities.
And it had two initial major consumer-facing use cases, didn't it? Guitar effects, processing, and gaming audio. How does it excel in those areas? What kind of impact did it make?
Precisely. For guitar effects processing, it leverages that powerful DSP for professional grade effects. We're talking distortion, reverb, sophisticated amp modeling. This allows musicians to achieve genuine studio quality tones, but without needing bulky, expensive physical pedal boards.
Right, just plug your guitar into this little USB box.
Essentially, yeah. And the latency here is incredibly low, less than 1 millisecond with the right drivers, like ASAO. That's absolutely critical for live performance. Any delay is immediately noticeable and can really throw off a musician's timing.
I could add.
Plus, its open source customization aspect means musicians can tweak, create, and share their own effects and presets. It fosters a vibrant community around the device, much like DCF is building its FOSS community. This is genuinely a game-changing tool in a market valued at nearly $1 billion, making high-end audio processing accessible and customizable for a much wider audience.
Okay, that's compelling for musicians.
All right.
What about for gaming audio? How does it enhance that experience beyond just standard stereo sound?
For gamers, it's really about pushing the boundaries of immersion and meaning a competitive edge, frankly. The device offloads complex ray-traced audio computations.
Ray-traced audio, like ray tracing for graphics?
Sort of, yeah. It simulates realistic sound propagation in 3D environments. It takes into account things like HRTF, head-related transfer function. It creates binaural 3D audio. That sound is coming from specific directions around you, makes you feel truly enveloped in the game. It also handles occlusion filtering, so sounds get realistically muffled if they're behind a wall, just like in real life. And dynamic effects like Doppler shifts as objects move past you.
So you can really pinpoint where sounds are coming.
Exactly. Players consistently report outstanding 3D audio capabilities and unmatched realism. It dramatically improves situational awareness. Think hearing an opponent's footsteps accurately and knowing precisely where they are, up, down, behind you. It provides RTX audio-like benefits that kind of advance spatial audio, but without needing those premium, expensive GPUs.
So it democratizes that advanced audio too.
Precisely. Bringing high-fidelity spatial audio to a much broader segment of the massive $184 billion gaming industry. It truly transforms the auditory landscape of gaming.
Okay, so powerful consumer applications. But beyond those, it also has a strong open source hardware strategy, right? FOSS. You mentioned it mirrors companies like Framework, known for their repairable modular laptops.
Right.
How does DeMoD apply this FOSS approach to their device, and what are the implications?
Yes, this is a very refined and strategic approach. It really highlights DeMoD's commitment to community and long-term sustainability. They plan to release full schematics, PCB layouts, and firmware for the base USB DSP device under the CERN Open Hardware License v2.
CERN OHL v2.
Okay. It's a highly permissive open source hardware license. It actively encourages the community to remix, adapt, modify the hardware for new applications. Things like drone diagnostics, maybe custom audio solutions, without needing a complete redesign of the core board every time. However, it's a tiered approach. They use these controls strategically to protect certain sensitive elements.
Like the ITAR regulated parts.
Potentially, yes. Or specific core DSP algorithms they want to keep proprietary, perhaps for performance reasons or licensing. They might use open source equivalents for algorithms that aren't subject to export controls, for instance. It cleverly balances openness with the need to protect strategic intellectual property. Furthermore, it features an advanced modular hardware design, heavily inspired, as you said, by Framework's expansion cards.
So you can swap parts in and out.
Exactly. Users can swap modules for specific functionalities. Imagine slotting in a Canvas module for automotive diagnostics, or a Modbus module for industrial automation, or even biosignal acquisition modules for healthcare applications. This means the same core device can be adapted for incredibly diverse markets without needing a complete redesign each time. That dramatically increases its versatility and lifespan. The overarching goal is clear: build a robust, community-driven ecosystem. They're planning a DeMoD Dev Hub on GitHub, complete with giveaways and contests, aiming for something like 500 contributors by year 2.
Leveraging the community for innovation.
Precisely. This significantly reduces DeMoD's own development costs by tapping into community innovation, and it fosters a sustainable, evolving platform that constantly finds new uses driven by the users themselves.
DeMoD's universal diagnostic platform, the plug-in revolution.
Okay, so DeMoD has this incredibly powerful USB DSP device, very flexible, and the wonderfully adaptable DCF communications framework. Now, what I find really compelling, maybe the most interesting part, is how these pieces, originally rooted in high-performance audio and secure communication, suddenly become a universal diagnostic platform. That leap seems quite significant. How does that transformation actually happen? This is where, as the sources say, it gets really interesting.
This is indeed the nexus of DeMoD's broader impact. It's a brilliant example of cross-domain innovation, taking tools from one area and applying them elsewhere. The fundamental insight here is that the open source nature of both the hardware FOSH and the software FOSS means they're not locked into a single purpose. They can be endlessly adapted.
Right, they're not just audio tools anymore.
Exactly. The DSP device, while initially audio-focused, is at its core just a powerful, real-time signal processor. It's like a mini supercomputer specifically designed for crunching numbers on incoming data streams, regardless of whether that data represents sound waves or telemetry from a car or vibrations from a machine. So when you combine this powerful, flexible hardware with DCF's modular, low-latency data exchange capabilities, and then add a comprehensive plug-in ecosystem, it transforms. It goes from being an audio processor to an incredibly versatile, multimodal diagnostic hub, capable of analyzing a vast array of sensor and telemetry data from pretty much any source imaginable.
The coalescence for diagnostic processing, as our sources call it. How does that synergy actually work in practice? How does it turn all that raw data into actionable insights?
Exactly. Coalescence is a good word for it. It's a three-pronged, highly synergistic approach that leverages the unique strengths of each component. First, you have data acquisition. This is where specialized plugins are key. They allow the system to collect an incredibly diverse range of data. This could be acoustic data, like the distinct hum of an engine or the subtle sound of a pipe leak.
Listening for problems.
Precisely. Or it could be telemetry from vehicle sensors, industrial machinery, even biosignals from the human body. These plugins interface with virtually any input source, wired connections like CAN bus, wireless protocols like Zigbee, ensuring no data point is out of reach. Second, real-time processing. Once the data is acquired, the DSP device handles the heavy lifting. It takes these raw data streams and performs compute-intensive tasks with lightning speed. Things like fast Fourier transforms FFTs for detailed frequency analysis. That's crucial for identifying specific vibrations or acoustic signatures of a fault.
Like finding a needle in a haystack of noise.
Exactly. Advanced filtering to remove noise and isolate critical signals, sophisticated anomaly detection algorithms. All of this happens with that sub-5 millisecond latency, almost instantaneous. And critically, remember, it offloads that significant 20-30% of the processing burden from the host CPU.
Right, freeing up the main system.
Which means complex diagnostics can run without slowing down the primary device or system.
Yeah.
And third, networked exchange. Once the DSP has processed this raw data and derived actionable insights, not just raw data anymore, but the intelligence derived from it, DCF takes over. It routes these insights reliably and scalably via its specialized transport plugins. This ensures less than 1% overhead maximum data throughput, and its self-healing redundancy keeps everything connected, even in dynamic or challenging environments where traditional networks might fail. This synergy turns what could be a confusing torrent of raw data into precise, actionable intelligence. It allows for unprecedented diagnostic capability, really.
And the customization potential for this whole system must be huge then, given that open source FHFOS foundation?
Absolutely huge. The FOSH foundation is critical here because it allows for an almost limitless degree of customization. Tailored algorithms can be developed and deployed by the community, allowing for incredibly specific diagnostic capabilities that target niche problems or even proprietary systems. This also directly helps avoid vendor lock-in.
Which is a major headache in many industries, right? Expensive proprietary tools.
Exactly. A major, costly problem. DeMoD's approach avoids that. This synergy turns raw, disparate data into actionable insights. For example, it can correlate acoustic data from a motor with telemetry data from its internal sensors to pinpoint a fault with far greater precision than either data source could offer alone, allowing for predictive maintenance that's both granular and holistic.
Okay, this plugin ecosystem sounds like the real linchpin, the game changer for these cross-industry applications. It essentially opens up DCF to communicate with almost anything, doesn't it? Could you maybe walk us through some of the most critical new additions to these plugins and how they enable this truly universal diagnostic capability?
That's precisely it. The expanded plugin set significantly enhances DCS transport layer. It effectively transforms it into a protocol chameleon, as you said earlier. It can integrate with a remarkable variety of systems and protocols.
Yep.
And what's particularly impressive is the speed of development here. Many of these key plugins like Canvas, Bluetooth, Modbus were created or significantly updated just weeks ago, according to our sources.
Wow, really responsive?
Incredibly responsive to diverse market needs. Let's look at a few key examples and what they unlock. I2S, inter-IC sound. This one's crucial for streaming high-fidelity audio, makes it perfect for acoustic diagnostics. Think of it as the system's ears, listening to machinery or biosignals.
Okay, the audio input.
Canvas, controller area network. Absolutely essential for interfacing with automotive ECUs, the car's internal network. Lets you pull critical telemetry like RPM, temperature, OBD2 codes directly.
The Car Whisperer plugin.
Bluetooth, obvious one, but vital. Enables wireless data exchange, connecting to countless sensors and IoT devices without cables. Offers flexibility for remote monitoring, mobile apps. Modbus. This is the workhorse for industrial automation. With this plugin, the system can talk directly to PLCs in factories, gathering operational metrics from heavy machinery.
Talking to the factory floor.
QUIC, quick UDP internet connections. This provides low-latency, secure, UDP-based communication. Ideal for cloud and edge computing where speed, security, and handling network changes are key. SCTP, Stream Control Transmission Protocol, offers reliable multi-stream transport, perfect for high-throughput diagnostics when you have lots of data coming in simultaneously from multiple sensors. Serial, RS-232-485, vital for backward compatibility, connects to older legacy devices using traditional serial standards, ensures broad compatibility with existing equipment.
Good for older factories or labs.
Unix socket, named Pipe. These are for ultra-fast local communication within a single host or edge device. Minimizes latency when data doesn't need to leave the system. Great for rapid processing on-site. Zigbee powers low-power IoT networks. Ideal for remote sensor arrays where battery life is critical. Allows for vast distributed data collection efficiently. IRC, Internet Relay Chat. This is a surprisingly powerful one. Allows diagnostics via chat-based protocols. Facilitates remote collaboration engineers sharing diagnostic logs in real time via chat.
Diagnostics over chat. Interesting.
Then there's Doom UDP, a custom low-latency UDP transport inspired by the networking of the game Doom, believe it or not. Designed for real-time telemetry in dynamic environments, maybe critical drone diagnostics where every packet counts.
Okay, that's unexpected.
And finally, the Unified Dual Transport. This one's particularly innovative. It allows the system to combine two transports simultaneously, like Canvas and I2S, for hybrid data streams.
So getting data from two sources at once seamlessly.
Exactly. Offers truly holistic data acquisition. Imagine hearing the engine while simultaneously reading its internal sensor data through Canvas. This comprehensive and rapidly expanding plug-in ecosystem makes DeMoD's system incredibly flexible, truly a universal hub for virtually any type of diagnostic data you can imagine. It effectively breaks down those communication barriers between disparate technologies and industries.
Industry deep dive, DeMoD's transformative impact.
Okay, now that we understand how these powerful components, the DSP, DCF, the plugins, all coalesce, let's really dive into how DeMoD's technology can transform specific industries. Diagnostics are absolutely critical in the automotive sector. You mentioned Canvas already. This platform could genuinely revolutionize car repair and maintenance. What does that future actually look like for car owners and technicians on the ground?
Indeed, it represents a profound shift. We're moving far beyond just plugging in a basic OBD2 scanner and getting a cryptic code. Imagine a truly comprehensive, multimodal diagnostic workflow for your vehicle. For data collection, the I2S plugin, as we discussed, captures the nuanced sounds engine hum, cabin noise, allows the system to listen for subtle cues, misfires, bearing wear, weird rattles, things that might indicate a developing problem long before it becomes serious.
Catching things early.
Exactly. Simultaneously, the Canvas plugin pulls an exhaustive array of critical ECU telemetry RPM, engine temp, fuel trims, precise OBD2 codes, transmission data, everything. Bluetooth effortlessly connects wireless sensors like modern BLE tire pressure monitors, maybe even aftermarket sensors you add, gathers additional contextual data. And remarkably, even legacy serial or Modbus devices can interface, meaning older vehicles or specialized diagnostic tools already in a service bay aren't left out.
So it integrates new and old tech.
Right. Then for processing. The DSP device takes this torrent of raw data and applies real-time, sophisticated algorithms. Performs those FFTs and wavelet transforms on the audio to detect subtle harmonic distortions indicating mechanical faults. applies fewer filters to isolate specific sounds of concern, all happening with that crucial sub-5 meters latency for instantaneous feedback. And for networking, DCF takes these processed results, again, the intelligence, not just raw data, and routes them reliably, maybe via P2P networks using Zigbee for fleet vehicles, allowing them to communicate status to each other or a central hub, or more likely via QUIC for secure, low-latency communication to cloud dashboards used by OEMs or diagnostic centers. The system's IUA mode can even dynamically assign roles for optimal data flow, ensuring everything gets where it needs to go efficiently, even in a busy garage.
That's a lot of data flowing. Can you give us a more concrete example? Maybe for an electric vehicle, since their mechanics and diagnostics are quite different from traditional combustion engines.
Absolutely. EVs present new diagnostic challenges, and this system seems well suited. Picture an EV repair shop. The I2S plugin records the unique motor hum or inverter whine of an electric drive unit. The DSP processes this audio in real time using FFT analysis to identify specific acoustic signatures, maybe that high-pitched whine that often indicates bearing wear in the electric motor.
Okay, listening for EV-specific sounds.
Right. Simultaneously, the Canvas plugin collects real-time battery data voltage, temperature cell by cell, current draw, state of charge, plus motor speed and torque data, all crucial for EV health. Then, these disparate data points are correlated. This is key. Say, matching specific noise patterns from the motor to unusual voltage sags or temperature spikes in a particular battery module. This allows prediction of maintenance needs with remarkable accuracy, often long before a catastrophic failure or even a warning light.
Predictive maintenance for EVs.
Exactly. Bluetooth might stream tire sensor data to monitor alignment, crucial for EV range, or even cabin sensor data related to the heat pump system. And all this processed, correlated information gets sent securely via QUIC to a cloud OEM dashboard or a technician's tablet with sub-10 meters latency, giving manufacturers or service centers an immediate, holistic, and predictive view of the vehicle's health. The Unified Dual Transport plugin is perfect here, combining I2S audio and Canvas data for that truly holistic analysis, hearing and seeing the problem simultaneously.
So what are the tangible benefits for, the average car owner or the technician in this shop? What do they get out of this comprehensive system beyond just reading a code?
The benefits are substantial, really multifaceted. For you, the car owner, it means comprehensive diagnostics using multimodal data. By combining acoustic, telemetry, and wireless sensor readings, this approach can lead to, as our sources suggest, a 20-30% higher accuracy and fault detection compared to just relying on OBD2 codes alone.
That's a big jump in accuracy.
It is. It translates to more precise repairs, less guesswork for the technician, fewer repeat visits for you, and ultimately, a more reliable vehicle. For the technician and the shop owner, it's incredibly cost-effective. Remember, the DeMoD device is projected at $5,100. That's dramatically less than proprietary single-purpose scanners that can cost hundreds, even thousands of dollars. Plus, its FOSS nature allows for free customizations, maybe specialized EV diagnostic algorithms, custom fleet monitoring routines. It democratizes access to high-end tools.
Levels the playing field for smaller shops.
Absolutely. Then there's the low latency, under 5 meters for I2S audio, under 10 meters for Canvas data. This enables real-time alerts. Imagine getting an immediate, accurate warning about a critical fault, not just a vague check engine light days later. DCF's reliability, with its self-healing, ensures continuous uptime, even in a mobile environment like a moving vehicle or a busy shop floor with wireless interference. And it's highly scalable. It supports fleet diagnostics via Zigbee or QUIC, aligning with and potentially disrupting the massive, growing $40 billion plus global auto diagnostics market, which is expanding at 5-7% annually. This isn't just about fixing cars better, it's about making them safer, more efficient, more affordable to maintain, and maybe even extending their operational lifespan.
Okay, powerful implications for automotive. Now, beyond cars, how does this technology translate to factory floors? Heavy machinery. You mentioned earlier that downtime there can be incredibly costly, sometimes millions of dollars an hour. This sounds like predictive maintenance on steroids.
Absolutely. This is where DeMoD's tech offers truly transformative predictive maintenance capabilities. Moving way beyond scheduled, often unnecessary, parts replacement to condition-based proactive intervention. Consider the use case. Monitoring critical high-value machinery. Industrial turbines, massive conveyor belts, complex robotic arms, and a smart factory. The goal is detecting those subtle signs of wear or impending failure long before they cause a complete, costly breakdown.
Preventing the $1,000,000-an-hour problem.
Precisely. Here, specialized plugins are indispensable. The I2S plugin captures minute vibration audio, maybe the distinct sounds of gears starting to grind, subtle changes in resonance, often telltale signs of mechanical stress or imbalance. Modbus, the industrial workhorse protocol, gathers vital PLC data directly from the machine's control systems: temperatures, pressures, operational cycles, error codes. Zigbee connects an array of low-power wireless sensors strategically placed on hard-to-reach or moving machinery components, providing distributed data without complex, vulnerable wiring runs. And SCTP, with its reliable multi-stream capabilities, handles the potentially high-throughput data streams heading to central monitoring servers, ensuring no critical operational data is lost, even during peak production times.
So grabbing data from everywhere on the machine.
Right. The implementation then involved the DSP device processing that I2S audio in real time, performing sophisticated spectral analysis, maybe for cavitation detection in pumps, or identifying specific frequency shifts indicative of bearing failure in a motor. Modbus continuously collects operational metrics from the PLCs. Zigbee streams data from remote sensors, maybe in dusty or electromagnetically noisy environments. All of this information is reliably fed through DCF's resilient self-healing network, which is crucial for maintaining connectivity in those challenging industrial environments where traditional Wi-Fi might struggle. The benefits are direct and substantial. Primarily, it reduces costly downtime. That potential $1 million per hour figure in some auto plants is a stark reminder of the stakes. By predicting failures accurately, maintenance can be scheduled proactively during planned shutdowns rather than reactively in an emergency situation that halts the entire production line.
Saving huge amounts of money and lost production.
Exactly. And the FOSS nature allows for custom algorithms tailored to specific machinery, even older, legacy equipment, or highly specialized custom machines. This avoids the expensive proprietary software lock-in that often comes with vendor-specific diagnostic tools. It democratizes sophisticated predictive analytics, making it accessible perhaps even to small and medium manufacturers who previously couldn't afford those big proprietary condition monitoring systems. And DCF's redundancy ensures reliable factory networks, preventing data loss that could lead to missed fault detection. It makes the whole process more robust.
Okay, from powerful machines to, delicate human bodies. How can this platform help in healthcare? Real-time, accurate data there can literally be life-saving. How does this potentially make medical diagnostics more accessible and precise?
Yeah, this raises an extremely important call about democratizing medical diagnostics, maybe even reaching underserved areas. DeMoD's platform offers significant potential here. The use case is analyzing various biosignals. Think heart sounds captured by a digital stethoscope, lung sounds, maybe even processing data from portable ultrasound devices, with a focus on real-time interpretation and assistance.
Augmenting the doctor's senses almost.
In a way, yes. Here, the plugins are tailored for medical data acquisition. I2S is perfect for high-fidelity audio input, streaming digital stethoscope data directly to the DSP for analysis. Bluetooth connects seamlessly to a growing range of wearable sensors, continuous pulse oximeters, ECG patches, blood glucose monitors, smart patches collecting skin temperature or sweat analysis data. QUIC provides secure cloud telemetry, allowing potentially sensitive patient data to be shared securely with specialists anywhere in the world or integrated into telemedicine platforms while adhering to strict privacy standards like EPUB. And Unix sockets could enable ultra-high-speed local processing and integration with existing hospital information systems or electronic health records, EHRs, ensuring diagnostic insights flow smoothly into clinical workflows without network latency becoming a bottleneck.
So connecting wearables, stethoscopes, and hospital systems.
Right. For implementation, imagine I2S streaming heart sounds to the DSP. The DSP performs real-time filtering to remove noise and applies advanced algorithms for things like murmur detection, classifying arrhythmia patterns, or perhaps detecting specific crackles or wheezes indicative of lung pathologies. Bluetooth pulls continuous data from wearable devices, providing a constant stream of vital signs for patient monitoring, maybe at home or in a post-op setting. QUIC then securely sends process results, alerts, or summaries to telemedicine platforms or remote monitoring centers, allowing doctors to oversee patients from afar or consult with specialists. The Unix socket would push these AI-assisted diagnostic insights directly into the patient's EHR in real time. The benefits are pretty clear. This enhances diagnostic precision by providing real-time analysis of subtle biosignals, potentially catching issues earlier than periodic manual checks or less sophisticated devices. It offers low latency, often less than 1 millisecond needed for processing certain signals, which is critical for acute care monitoring or situations where rapid intervention can be life-saving. And importantly, its open-source nature supports seamless integration with evolving medical standards and regulations. It allows for community-driven development of new diagnostic algorithms, perhaps validated AI models for specific conditions, or even ruggedized versions for deployment in low-resource settings where expensive proprietary equipment is simply out of reach. It fundamentally makes sophisticated medical diagnostics potentially more widely available and adaptable.
Okay, let's shift gears to the Internet of Things, IoT. It's all about vast networks of connected sensors gathering data from, well, everywhere. How does DeMoD fit into that world, particularly for large-scale environmental monitoring or maybe checking the integrity of critical infrastructure like bridges or pipelines, where cost and reliability over wide areas are key?
In IoT and environmental monitoring, DeMoD provides a potentially powerful, low-cost, and incredibly resilient backbone for these extensive sensor networks. It addresses challenges that traditional systems often struggle with, like power consumption, cost, and network reliability in remote areas. The use case could be detecting pipeline leaks across vast remote terrains using acoustic sensors, or continuously monitoring the structural integrity of bridges, buildings, dams, or other critical infrastructure using vibration, strain, and acoustic data.
Finding problems before they become disasters.
Exactly. Relevant plugins here are chosen for their efficiency and reach in these scenarios. I2S connects sensitive acoustic sensors, which can pick up the distinct, often faint sound of a minute gas leak or the microcracking sound signature of stress developing in a concrete structure. Zigbee is ideal here, powering low-power IoT networks. It makes deploying hundreds, even thousands, of battery-operated sensors across a wide geographic area feasible, where running power and cables is impractical or prohibitively expensive. Serial allows integration with older, legacy environmental sensors, maybe weather stations or water quality monitors that are already deployed but lack modern connectivity. Ensures existing infrastructure can be brought into the smart network. And named pipe or Unix sockets handle local edge processing. Data from a cluster of sensors might be processed on-site by a local DeMoD device, minimizing the amount of raw data that needs to be transmitted over potentially costly or unreliable cellular or satellite links. Only the important insights get sent upstream.
Smart processing at the edge.
Right. The implementation involves the DSP analyzing I2S audio for specific leak signatures in that pipeline example, or identifying changes in the resonant frequency or microvibrations indicative of structural stress in a bridge. Zigbee streams aggregated sensor data from these remote locations, forming a robust mesh network that can self-organize and route around failed nodes. DCF then ensures these remote sites maintain continuous connectivity back to a central monitoring system, leveraging its self-healing capabilities even if some nodes go offline temporarily or network conditions are poor. Data collection remains uninterrupted. The benefits are significant, particularly the low-cost solutions. Again, that $5,100 DSP device compared to $500 plus for many proprietary industrial IoT gateways or data loggers. This makes large-scale deployments for environmental monitoring or infrastructure integrity checks vastly more economically viable, especially for public works or research projects. It reliably supports remote sites, overcoming a major challenge for traditional connectivity solutions. And it aligns perfectly with the burgeoning $50 billion plus global IoT market, providing a flexible, high-performance, and affordable foundation that can be customized for anything from precision agriculture sensing to monitoring urban air quality or managing smart city infrastructure.
Okay, now for perhaps the most demanding environment, aerospace. This is an industry where reliability, precision, safety, and minimizing weight are absolutely paramount. There's just no room for error. How does DeMoD's platform address the unique, mission-critical challenges of flight-critical monitoring?
This is truly a mission-critical application domain, yeah. The stakes are incredibly high, every detail matters immensely. DeMoD's technology brings a unique combination of precision, its compact size, and that crucial customizability to this sector. The use case is continuously monitoring aircraft engines during flight for subtle signs of wear or impending failure, detecting minute faults in turbine blades before they propagate, or maybe even assessing the integrity of the airframe itself using distributed sensors during flight, or as part of rigorous pre-flight checks. Early detection here can prevent catastrophic failures.
Safety is number one.
Absolutely. Key plugins are selected for their performance and relevance in this demanding environment. I2S is used for engine audio analysis, listening for subtle changes in the engine's hum, specific vibration patterns, or acoustic anomalies that could signal a developing mechanical issue undetectable by standard sensors alone. Canvas is absolutely crucial here, just like in cars, but often more complex. think air and sea standards. It collects vast amounts of real-time sensor telemetry from the engine's control units, FADECs, flight control computers, and other aircraft systems. And for communication, perhaps back to the cockpit or down to ground stations, QUIC would be a strong candidate for its low-latency secure features. Or even that custom DeMoD might find a niche here for its absolute minimal overhead in streaming critical telemetry in real time, perhaps over constrained satellite links where every byte counts.
Sending vital signs from the plane.
Exactly. The implementation involves the DSP processing that I2S audio for detailed spectral analysis, identifying minute frequency shifts that could indicate a developing crack in a turbine blade, or the loosening of a critical component long before it causes a major imbalance. Canvas collects vital sensor data, temperatures, pressures, rotational speeds, fuel flow, vibration levels with high precision and reliability. QUIC or DoomUDP then streams this critical telemetry and the process diagnostic insights in real time to ground crews or potentially directly to maintenance systems. This allows for proactive maintenance decisions, informing pilots of potential issues, and in extreme cases, potentially enabling decisions to divert flights if a critical issue is detected early enough. The benefits are profound and primarily focused on safety. It significantly improves safety through early, often predictive, fault detection, potentially preventing catastrophic failures that cost lives and astronomical amounts of money. The compact size of the DSP device reduces onboard weight compared to bulky traditional diagnostic equipment or data recorders. That's a major advantage in aerospace, where every gram saved translates to fuel efficiency and improved performance. And the FOSS nature, again, allows for proprietary adaptations for sensitive defense applications. Government agencies or aerospace manufacturers can take the open source baseline and build their own custom, secure, highly specialized diagnostic and monitoring solutions without being locked into a single, potentially foreign vendor. It gives them control and auditability over their own mission-critical systems.
Okay, one last area, remote collaboration. We know remote teams are more common than ever, especially in specialized fields like diagnostics, where the real expert might be halfway across the world. How can this platform facilitate truly effective collaboration for diagnostic teams spread across different locations, maybe even different time zones?
Yeah, for global diagnostic teams, whether they're supporting aircraft, complex industrial machinery, or even remote medical devices, it's all about breaking down communication silos and data sharing barriers, enabling a truly collaborative, real-time problem-solving environment. The use case is enabling these geographically dispersed diagnostic teams to collaborate effectively, share real-time data seamlessly, maybe even integrating diagnostic information into familiar communication tools like chat platforms, allowing engineers in different time zones to work on the same complex problems simultaneously, looking at the same data.
Bringing the experts together virtually.
Exactly. Here, the IRC plugin is a surprisingly effective and highly adaptable tool. It allows for structured, chat-based data sharing. You could use it to stream diagnostic logs, system alerts, and structured team discussions in a way that's familiar, low overhead, and easily archived. And combined with the unified dual transport plugin, it could merge IRC with, say, QUIC for hybrid streams.
How would that work?
Well, you could have the high bandwidth, real-time diagnostic data like sensor readings or audio streams flowing via QUIC into shared dashboards or analysis tools, while simultaneously human-readable logs, expert commentary, diagnostic steps taken, and team discussion are being exchanged in a structured chat format via the IRC plugin. The implementation means IRC streams diagnostic logs, alerts, and team discussions to remote team members in a structured, accessible way, providing a persistent record of the diagnostic process itself. While QUIC ensures high-performance data exchange for the raw or processed telemetry feeding into shared analysis tools, creates a multi-channel communication and data hub specifically for diagnostics. The benefits are significant. This directly facilitates global collaboration, enables experts from anywhere in the world to contribute their knowledge to a diagnosis, bringing diverse perspectives and specialized skills to bear on complex problems, leading to faster resolutions. And being open source, it allows for seamless integration with existing tools and workflows. Teams don't necessarily have to adopt entirely new proprietary communication platforms just for diagnostics. They can potentially integrate DeMoD's capabilities into the tools they already use. It essentially democratizes specialized knowledge, making it more global and collaborative, allowing faster resolution of critical issues and better sharing of diagnostic best practices across an organization or even an entire industry.
The bigger picture, why this matters for you.
Okay, so we've covered a lot of ground. We've gone through the tech, the origins, the plugins, and explored applications across, wow, Automotive, manufacturing, healthcare, IoT, aerospace, collaboration. What's the overarching takeaway here? For you, our listener, who just wants to understand the real significance of DeMoD's technology and how it might genuinely impact the future, what's the big picture?
Yeah, that's the crucial question, right? How does DeMoD approach this combination of open source, high performance, low cost, and adaptability, potentially redefine what's possible for innovation and access across such a diverse landscape? The collective benefits are truly compelling, I think, and they boil down to a few key areas that profoundly impact how we might approach diagnostics and real-time systems in almost every aspect of modern life. First, and maybe most fundamentally, it enables true multimodal diagnostics. You're not just getting one piece of the puzzle anymore, like just an error code.
Yeah.
You're getting a holistic, interconnected view. By seamlessly combining diverse data sources, acoustic signatures, precise telemetry, wireless sensor readings, maybe even visual data down the line, it leads to that significant estimated 20-30% improvement in fault detection accuracy.
Seeing the whole picture, not just a snapshot.
Yeah, exactly. This isn't just a marginal gain. It means more reliable systems, safer operations, far more efficient maintenance across the board. Whether it's your car, a critical factory robot, monitoring a patient's health, or ensuring an aircraft engine is safe. It's about getting to the root cause faster and with much greater certainty. Second, there's the unparalleled performance. We're talking sub-millisecond latency for communication, less than 1% overhead, combined with that significant 20-30% CPU offload on host devices thanks to the dedicated DSP. This isn't just fast in an abstract sense, it's genuinely real-time. It enables critical applications that simply weren't feasible before without dedicated expensive hardware. It allows systems to react before a problem escalates, provide instantaneous feedback to a musician or gamer, or monitor a patient with continuous, ultra-responsive data streams without bogging down the primary systems.
Performance that enables new applications.
Precisely. Third is the extreme flexibility and adaptability. That plug-in system truly makes this a protocol chameleon, as we said, supporting virtually any communication standard imaginable: Canvas, Modbus, Zigbee, QUIC, I2S, even legacy serial or custom protocols like these. And its boss-fosh nature allows for infinite customization. Developers, researchers, hobbyists, companies, they can all develop specific algorithms, maybe integrate cutting-edge AI-based anomaly detection models, perhaps through community contributions without ever being tied down by expensive vendor lock-in or restrictive licenses. This adaptability future-proofs the technology, allowing it to evolve organically with new challenges and new hardware capabilities.
Freedom to innovate on top of it.
Absolutely.
Yeah.
Fourth, and this is perhaps one of the most significant and potentially disruptive aspects, is its disruptive cost effectiveness. You're looking at a multi-purpose diagnostic and processing tool priced at $5,100 that, in many specific applications, can likely outperform proprietary single-purpose solutions costing $200, $500, or even thousands of dollars. This isn't just about saving money for large corporations, though it does that too. It fundamentally democratizes access to high-end diagnostic and signal processing capabilities. It makes these powerful tools potentially available for individuals, small businesses, educational institutions, startups, and massive enterprises alike. It levels the playing field for innovation and problem-solving globally.
Bringing high-tech capabilities within reach for many more people.
Exactly. And finally, there's reliability and sustainability. With DCS built-in self-healing network capabilities and the compact, relatively low-power USB-powered DSP device, you get solutions that are inherently robust and energy efficient. They're built for longevity. And the vibrant open-source community fostered around both the hardware and software ensures it's not just a static product, but an evolving ecosystem designed to endure, adapt, and continuously improve over time, driven by its users' needs.
So, putting it all together, what does this really mean for us, for how innovation happens? It feels like a powerful testament to how open source innovation, driven by genuinely accessible hardware and incredibly adaptable software, can create truly disruptive solutions. It shows us, maybe, that groundbreaking technology doesn't have to be prohibitively expensive or locked away behind proprietary walls and EPAs. Instead, it seems it can empower almost anyone, from a single-driven, self-taught developer like Asher Leroy, bootstrapping a company, to a global community of contributors to build the tools that profoundly impact how we interact with technology and solve complex, real-world problems. It feels like it redefines what's possible, not just for large enterprises with huge R&D budgets, but maybe even more significantly, for the individual innovator, the small team, the researcher, the hobbyist. Outro. Wow, what an incredible deep dive into DeMoD's technology and its potential impact. From Asher Leroy's truly impressive solo journey, self-taught, bootstrapping a company by 21, tackling complex audio latency, to the intricate and, as we've seen, rapidly evolving DeMoD communications framework. Yeah. And that versatile multi-purpose USB DSP audio device. We've really seen how these innovations, especially when combined with that expansive plug-in ecosystem, are creating something potentially transformative, a universal diagnostic platform.
Yeah, we've explored how this system, this combination of hardware, software, and open source philosophy, is poised to revolutionize so many industries, significantly improving fault detection in your car using multimodal data, enabling truly transformative predictive maintenance in factories to slash that costly downtime, enhancing precision and, importantly, accessibility in healthcare with real-time biosignal analysis, empowering smarter, more resilient IoT networks with low-cost, reliable sensors for environmental or infrastructure monitoring, ensuring critical safety in demanding fields like aerospace with flight-critical monitoring, even facilitating seamless global collaboration for diagnostic teams, bringing expertise together regardless of location. It really is a fascinating convergence of high performance, remarkable affordability, extreme adaptability, and that powerful force of community-driven innovation. It stands to benefit countless applications and individuals in ways we might not even fully grasp yet.
And here's where it gets truly thought-provoking, maybe the final thing to leave you with. Consider how this accessible, highly customizable, and yet high-performance diagnostic platform fundamentally empowers individuals and small businesses. It gives them the potential ability to tackle complex diagnostic and signal processing problems that were, until recently, almost exclusively reserved for large corporations with deep pockets or incredibly expensive, specialized proprietary systems. It genuinely seems to democratize high-tech diagnostics and complex problem solving. So, the question for you is, what problem in your world, maybe something good, maybe something small, maybe something at work, maybe a personal project, could a platform like this, putting these sophisticated tools within reach, help you uniquely solve? Thank you so much for joining us on this deep dive today. We hope you feel more informed and perhaps, like us, even a little inspired by the sheer power and potential of open innovation. Until next time, keep digging, keep learning.